Section 2.3 is almost entirely dedicated to this one huge question. Are there infinitely many prime numbers? Why or why not? Now, in order to start getting at this question, we need to review a little bit of algebra. Primarily, we need to review factor trees, this method for factoring out any big number into its prime factors. So I'm going to factor out 540. And remember, the first thing you have to do is just think of any number that you know 540 is divisible by. Now, for me, I see that 0, and I'm like, 540 is divisible by 10. So I write 54 times 10. I want to point out you don't have to think of prime numbers, right? Just anything. Just split that number up. Now, I have to split 54 and 10. Doesn't matter what order I do it. So 54 is even, right? So that means that 54 is 27 times 2. Now I've circled 2 because 2 is prime. I don't need to split it up anymore. 10 is equal to 5 times 2. Circle both of those. And 27, I remember, is 3 times 3 times 3. So I'm going to go ahead and split it all the way up all in one go. So this is how I know that 540 is equal to 2 to the 2 power times 3 to the 3 power times 5. And you can do this with any natural number. They can all be split up into a single unique product of primes. We're going to be operating with these definitions of prime and composite numbers. So if any number that's bigger than 1 can possibly be expressed as a product of two smaller natural numbers, then we're going to call that number composite. And if a number can't be expressed as a product of two smaller natural numbers, then it's prime. So another way to talk about primeness, I guess, is we know that every number can be factored down to prime numbers. And we also know that every number is divisible by 1 in itself. That's not special. That doesn't make a number prime. But if the only two factors of a number are 1 and itself, if those are the only two you can find, then you call that number prime. So here are some examples of prime numbers, right? 2 is the only even one, right? Because any other even number is going to be divisible by 2. But it's not true that every odd number is prime. Be careful about that. So here's some examples of composite numbers. A really easy way to generate huge families of composite numbers is pick your favorite prime number and start making multiples of it. So 4, 6, 8, 10, 12, 14, 16, those are composite. Multiples of 3, 6, 9, 12, 15, 18, 21, they're all composite. Multiples of 5, those are all composite. So again, do you see the odd numbers down there like 9 and 15 and 25? Be very careful. It's not true that odd numbers necessarily have to be prime. There's another number that's not prime. It's 1. We all just agreed in the math community that 1 was not going to be prime. One reason that this makes sense to claim is that we really like as a definition saying if the only factors of a number are 1 and itself, then it gets to be a prime number. And the thing about 1 is it doesn't even have two factors. It just has the one factor, right? 1 is its only factor. So we're not going to let that guy be prime. So now that we've hashed out some definitions, we could ask ourselves some questions that we might find interesting. For example, is there a smallest prime number? There absolutely is. And it's 2, not 1, right? 2 gets to be the smallest prime number. So there's a smallest one, but is there a biggest one? And that's really deeply related to the question, how many prime numbers are there? And the thing is, there's infinitely many. And you might be thinking, well, duh, that's common sense. There's infinitely many numbers, so there have to be infinitely many prime numbers. But that's not true. We have to be very careful about how we prove it.